Okay, today we're going to finish off Chapter 6, which, remember, was dynamics, motion along a line. The goal here was to learn how to solve linear force and motion problems. And as a quick note, we will not be covering the material from Section 6.4 on rolling friction. So the two main types of friction we will be covering is static friction and kinetic friction. So let's start with static friction. So here we have a shoe, and it's pushing against a sloped wooden floor, but it does not slip. Why not? Because on a microscopic scale, the bottom surface of the shoe and the top surface of the wood are rough. They're not perfectly smooth. So all the little points from the top and points from the bottom will touch one another, lock together, kind of like gears on a bike or something, and you'll have a pressing force, actually a normal force, which is due to the molecular bonds between the molecules pushing along one another. So this force is tangent to the surface, meaning parallel to the surface, as opposed to the normal force, which is perpendicular. So here's an example of a person pushing against a box, but the box is not moving. The object's at rest, velocity is 0, and it's not accelerating either. So since it's not accelerating, it must be in equilibrium. So if you draw a free body diagram, all the forces have to balance. In the vertical direction, the normal force upwards balances the gravity force downwards. But in the horizontal direction, you now have this external pushing force from the normal force of this woman's hands. So the static friction must exactly balance the pushing force. And so here's the equation for static friction in this case. Static friction points in the direction opposite to the way that the object would slip if there was no static friction. So if this was a super slippery floor with marbles on it or something, we know that the object would accelerate towards the right, but it doesn't because there's static friction pointing towards the left. So static friction acts in this case in response to an applied force. You've got the pushing force. If it's small, then there's a small amount of static friction. If it increases, then the static friction increases in response. Okay? And it can grow and grow until it reaches some maximum value when it will start slipping. So the object remains at rest as long as the static friction force is less than F sub s max, where F sub s max has an equation for it that we find through many experiments. It's mu sub s times n. This Greek letter, it looks like a U or something, is called mu, and it's called the coefficient of static friction. And the normal force, n, determines how big the maximum static friction force can be. Bigger normal force from the surface to the object, the bigger the maximum possible static friction. Okay, so the next most important type of friction is called kinetic friction, sometimes called sliding friction. So the example here is that the same woman's pushing this big crate or something, and now it's sliding along, it's moving relative to the floor. So now there is a kinetic friction opposing the velocity of this object relative to the floor. And that has a definite equation. It's always equal to mu sub k times the normal force. Looks sort of a similar equation for Fs max. But here the constant mu sub k is called the coefficient of kinetic friction. So here in this case we have a pushing force which is bigger than the kinetic friction force, so now there's a net force to the right, so the object will be accelerating. But the kinetic friction is always directed opposite to the velocity of the object relative to the surface that it's sliding along. And it turns out that for any particular pair of surfaces, the coefficient of kinetic friction is less than the coefficient of static friction. So here's some measured values of coefficients of friction. If you have rubber sitting on concrete, the coefficient of static friction is 1.00, and that's a dimensionless number, there's no units. The coefficient of kinetic friction is a little less, 0.80. If you have steel on steel, like the wheels on a train riding on train track with steel, then coefficient of static friction is 0.8, kinetic friction 0.6. If the rails are wet, okay, then the static friction drops way down to 0.1 and kinetic friction 0.5, so it's easier to slip. Wood on wood, wood on snow, ice on ice. Okay, when things are on ice, the coefficients of static and kinetic friction drop to be very, very low. Now we're very familiar with cars driving along the roads, but what's interesting is that if you slam on all the brakes for the car in such a way that you hear a big screeching sound and the car tires are sliding along the concrete, then that would be kinetic friction. But under normal driving conditions, the portion of the rolling wheel that contacts the surface is actually stationary. It's not sliding along. So as the wheel turns, this part of the tread gets laid down on the pavement, and this part of the tread gets picked up. But the part of the tread that's just touching the surface is actually not moving for just an instant. And it's certainly not sliding. So if your car is accelerating or decelerating or turning or something, it is the static friction of the road and the wheels that provides the net force which accelerates the car. So the actual causes of friction really are kind of complicated. It involves all the microscopic surface properties, but in this chapter we're using a model of friction, and it's a simplification of reality. And these are these two equations we learned. The static friction is whatever is necessary to prevent motion up to a maximum of mu sub s times n, and the kinetic friction is equal to mu sub k times n in the direction opposite the motion. Motion here always means motion relative to the surface. The force of kinetic friction is proportional to the normal force, and the maximum static friction is proportional to the normal force. That's what these coefficients mean. Lastly, we'll just show a graph here of the friction force on the vertical axis as plotted versus some pushing force. So that woman's pushing the crate, and we measure the response. So when the crate is at rest relative to the surface, we have a slope of 1 here. The static friction is equal to the pushing force. It starts off at 0. She's not pushing it. There's no friction. Friction increases, increases, increases up to some maximum value. That's just when it starts slipping. Once she gets it going, the friction force suddenly decreases and becomes a constant value. No matter how fast it's going or how hard she's pushing, if it's sliding, the friction force is equal to mu sub k times n. So section 6.5 is on drag. Drag is a complicated force. It's whenever an object moves through a fluid, there's a resistive force, kind of like a kinetic friction, which slows it down. So for example, this motorcycle going through the air is a fluid, and so it provides this resistive force. And it turns out that due to this fluid mechanics, faster objects experience a greater drag force than slower objects. So if a motorcycle is moving very slow, there's a very small drag force on it, but as it gets faster and faster, this drag force is significant. Drag is always opposite to the object's velocity through the fluid. So again, it's pretty complicated. Normally you use a computer model to try to determine what the drag is, but for normal sized objects on Earth traveling at a speed which is less than a few hundred meters per second, you can model air resistance with this equation, 1/2 c rho a v squared, where a is the cross-section area of the object, rho is the density of the air, which is about 1.2 kilograms per meter cubed. C is a dimensionless drag coefficient, usually sort of near 1, depending on the shape of the object. And V is the velocity. So here is an example of a falling sphere. So a sphere has a drag coefficient of 0.5. The cross-section area of a sphere is always pi r squared. It's a circular cross-sectional area. If you have a cylinder that's falling end down, now the cross-section area is pi r squared, where r is the radius of the cylinder, and the drag coefficient turns out to be 0.8. So you can look up in a table what the drag coefficient is for different shapes. A cylinder, if it's falling side down, has a drag coefficient of about 1.1. And here the area, cross-section area now, perpendicular to the velocity, is now that of a rectangle. I guess 2r would be this side, and L, the length of the cylinder, would be the other side. So 2RL would be the cross-section area. So once you have drag, there's an interesting concept which is terminal speed. So we know that as an object falls, it gets faster and faster. Well, if it's going slowly, there's no drag force. As it's going faster and faster, the drag force keeps increasing and increasing. And if the object falls fast enough, it'll eventually reach a speed at which the drag force equals the force of gravity, so that the net force is actually 0 at this time. So now the object is falling at a constant speed, which we call terminal speed. Acceleration equals 0. And if you solve out the equation we have for drag force equals mg, the force of gravity, you can find the terminal velocity is equal to the square root of 2mg over c rho a. So how does that look? Well, here's a graph of time, speed of an object versus time. So it's actually velocity, downward velocity. This straight line is what the velocity would be if there was no air resistance. It's just negative g is the slope of this. But in reality, with air, what happens is that there's an upward drag force which slows down the velocity so that it approaches asymptotically this terminal velocity. Okay, so I just wanted to end with chapter 6 with a little personal message to you. So section 6.6 from your textbook is called More Examples of Newton's Second Law. It just has a bunch of examples. Stopping distances, you've got a car which slams on the brakes and skids to a halt. You've got measuring the tension, pulling a cart, making sure the cargo doesn't slide, and there's even a challenge example, acceleration from variable force. So I really encourage you to work through some of these examples yourself. So learning to do physics problems, I think, is a little bit like learning to swim. You can watch someone else do it, and I guess that's a little instructive, but really it doesn't help you learn to swim. The only way to learn is to jump in the water, and what I mean by that is kind of go out of your comfort zone. You have to get some paper, get a calculator, get a pen, and try the problems yourself. So look at a problem, write it down, figure out how you're going to start. Usually start by drawing a diagram. Write down all the things you know, and then try to apply the equations, figure out where the forces are, try to solve for what the net force on the object of interest is, see if it's an equilibrium problem, make the net force balance to be 0. If it's a non-equilibrium problem, then you've got the net force equals mass times acceleration, and try to solve for your unknowns. So I say good luck, and I think you'll get better at this and develop your confidence as you work through these things.